Mike goes through the presentation.
All right, everybody, we're going to get started. Good afternoon. Thanks for coming out to our virtual meeting here. So as John mentioned, we're going to go through these spreadsheets, how they've been updated to interact with Revit. If you're in the meeting now, please mute your mic. I'm getting a little bit of noise from somewhere. John mentioned these spreadsheets are available on the internet now, so if you want to go over there and download them, you can follow along and take a look. So we're using Dynamo. It's an add-in to Revit. It's a programming tool. It's basically a graph, a block coding, like a flow chart, and we can take information from our models, export it to Excel, and manipulate it the way that we want to get the information that we need and help us with our calculations. So today we're going to talk a little bit about ductwork static pressure loss fundamentals. We'll get into pressure calculations, how to interface with Revit, and some of the important design variables that we take into consideration. We're going to do the same with pump head, and then we'll finish up with system volume and expansion tank sizing. So static pressure is directly related to surface material on the duct, obstacles. Static pressure is basically all the resistance that the air is going to face as it's moving through the ductwork system. It costs money to move air, so the higher static pressure, the more power it's going to take. We need to make sure everything is properly calculated. A bad fan or a fan that's not strong enough can cripple a system, especially at its most critical point, furthest away from the fan. We typically measure static in inches of water column. Just for reference, 1 inch of water column is about a third of a PSI. So where do we get pressure loss in a system? We have friction losses. This happens at the edge of the duct where you can assume the velocity of the air is zero. And keep in mind, a lot of the stuff that we're talking about here is about air, but it also applies to water. Both are fluids. So
Mike, yep. Mike, Johnny's here. Did you want to view your screen? We're looking at your video. Do you want your computer screen up?
Yeah. That would help. There we go. Thanks, John. So if we look at a flow profile in a duct, you can basically assume at the surface of the duct the velocity is zero, and then as the velocity increases toward the center of the duct, this area right here, the boundary layer, is where all your friction is going to be. And then we have dynamic losses. So this is going to be a result of changes in direction, shape of the ductwork, flow rate. So we're gonna take pressure loss from a bunch of different sources: the ductwork itself, fittings, diffusers and grills, dampers, filters. And here's just a good look of, if air is coming around a corner on an elbow in ductwork, it's going to want to work its way to the outside of the duct. This is why a lot of times mitered elbows have turning vanes to help with the pressure loss going around this corner. So when we're designing ductwork, typical rule of thumb is 0.1 inches of water column per 100 feet. Use your trusty ductulator to help with that. And then return system's a little bit less, 0.08 inches water column per 100 feet. It really depends on the application, though. Some applications, like a theater, require a very low air velocity. And so what we want to do when we're designing is we want to keep it in this laminar region. The air flows way better in this type of profile. That's controlled by a Reynolds number, which is this formula right over here. And we can control the diameter of the ductwork. And that helps us keep the velocities down and keep the flow laminar. Just really quick, we're going to talk about converging and diverging flows. It's pretty straightforward. If we're looking at, say, if this is a return system over here, bear with me. If this is a return system, and we are looking at a critical path that comes straight through here, you'll see that this is going to be a converging Y of a main. And then if we're a return system coming off a branch into a main, this would be a converging Y branch. You're going to see these different types of fittings on the static pressure spreadsheet. And then if it's a supply, if you're calculating your critical run going straight and there's a tap off to the side, this is a diverging Y. And then if you're going off, it's a diverging Y main, because you're not taking the branch, you're going straight through. And then if you're looking at your critical run that comes out on the shoe tap, this would be a diverging Y branch. So you're taking the branch. Take that off. So when we want to calculate pressure loss, there are a lot of equations and tables to determine the pressure drops through different sections. These tables and coefficients, they incorporate the dynamic and friction losses that we just talked about. It's very important to have the geometry, flow, convergence and divergence and fitting type right in these calculations, because these coefficients are based on that. The tables themselves are from Smackna and Ashray, and John has taken these tables and put them into his spreadsheet. Your user inputs, though, are what dictate what coefficients are used. So we're going to take a quick look at the spreadsheet. And so some new tabs have been added. John, do you want to kind of talk about how this spreadsheet has changed a little bit?
Yeah, from the old spreadsheet over here, I had some columns which were nodes. I've changed those to a fitting tag and a flow direction. The fitting tag or a section tag is specifically to work with the Revit, because as part of this setup, Mike will get into is, you're getting a tag number at each one of these fittings, and the spreadsheet then puts those in order of increasing number. So therefore, the fittings and everything goes into the spreadsheet in the order of flow as the air flows through the system. Over here, I blanked out various cells here, meaning you don't need to have information input. I think in the past there was some confusion as to when you put values in, when you don't put values in. So as you select a type of fitting, if it is looking for a value, that cell will now, the blank will go away saying, okay, I'm looking for a value. Specifically, there's been confusion, I think, regarding, diverging and converging Ys, what goes first, what goes second. Up here, I've tried to give you some information. If you're looking for a diverging Y, on the line that you're dealing with, you want the size of the branch and the airflow of the branch. For fitting 2, you want the size of the duct entering that fitting and the branch airflow. So these are sort of helping you just indicate, what information is on that line with regard to the duct size and the airflow.
Hey, John, I got a quick question on that.
Yes.
So looking at fitting 2, for example, like you said, it's a converging Y main. So you've got a branch going off to the right and then you've got
Yes.
your airflow straight through on your main.
Yes,
So if your critical run is your straight through main, you want the entering size of the Y fitting, and you want
Yes.
the airflow of the branch
right.
going to the right, even though you're still going down the main for critical, correct?
That is correct.
Okay, thank you.
And the formulas are put together to know that now we are looking at the airflow going down.
So when you put that branch airflow in, it'll automatically subtract that airflow and continue that straight through.
Yes, because it's going to now, instead of be looking at what airflow is here, I think it's going to be looking at what airflow is in the resultant continuing down. You know, it dictates which cell I'm going to take a look at with regard to airflow when I'm calculating the quantity of air in and out of the fitting, which is the QB, QC, QO, QI.
Okay, thank you.
So
I think that's most of the updates that I have there.
the pressure loss Revit tab is a little bit different. Whereas on the manual tab, you're going to input the fitting CFM that's taken off or added. On this spreadsheet, we are looking at on each row the exact CFM in that duct or fitting. So then we have a couple different examples. We have a Revit sample duct plan, the sample raw output that you would get from Revit based on that, and then a Revit sample final, which includes dampers, HVAC equipment, grills, etc., to make for a complete calculation. So this is here to look at. And then over here, I mean, these are just some of the tables we were talking about. You won't see these in the spreadsheet, but John is referencing these tables as you put your inputs in. It'll choose specifically for the fittings that have a variable coefficient, loss coefficient. It will choose the coefficient based on what you put in. The higher the loss coefficient, the more static pressure loss you're going to get.
And just to let you know, I mean, I don't have every single fitting table that exists in the ASHRAE or SMACTA manuals. I've just pulled out some of the most common values and the most common ranges.
And they are a touch on the conservative side, correct, John?
Yes.
This one has to keep doing that. All right, so the first thing we're going to do is determine the critical path. And sometimes you might have to do more than one critical path just to make sure that you're correct. Depends on the system. It's just going to be the path of air that's going to give you the highest pressure drop overall. And don't forget, in some cases, you have to take into account pressure drop from intake ductwork to intake louvers, penthouses, and the same with exhaust, louvers and penthouses. So how are you going to do this in Revit? We're going to model it. We're going to model the ductwork system, and we're going to isolate the critical run. There's a couple different ways you can do that. You can do a filter through a comment. You can add a comment to each piece on the critical run, call it calculation, and then you can filter your view based on that. You can feed other elements into the calculation, like annotations and etc. It will ignore them. So once we isolate the critical run, sometimes I like to just attach a model, open it, and then copy the critical run to a blank space and then work on it from there. So then we're going to fill in the calc node and calc flow parameter for each piece of ductwork, indicating the CFM and the node number. And we're going to open up Dynamo, put our user inputs in, select the critical run, and then the results will be exported to Excel. And as with any program, if you don't set it up right, it's not going to work right. The program has built-in checks so that you can understand, was there an error in this calculation? For example, if you miss a calc node or a calc flow parameter on one of the pieces of ductwork, the program's going to throw an error and let you know, hey, you missed one here. So the first thing you're going to do once you get it out of Revit is check over the calculation. You're going to put the temperature of your airstream in. The hotter the airstream, the harder it is to to push around with a fan. It's going to have a greater pressure drop. The dampers, add those in. Any pressure loss for grills, diffusers, louvers, penthouses. Any special conditions like abrupt inlet or outlet, equipment pressure drop, any other items pressure drop other than just the ductwork and the fittings. You're going to want to make sure you go through your calculation and put that in. Last thing you're going to do is go to the items not included. The program will output the elements that aren't included to a special tab on the spreadsheet. Take a glance through there, and we're going to take a look at that right now. So if we just take our test layout here, we have specific tags for this that you can do a tag all. My computer is going to be really slow right now. You can do a tag all operation on your critical run ductwork and choose the tag, the static head tag, and it'll tag each piece of ductwork and fitting so that you can get an idea of, hey, this is what I have here, this is what I have over here. Without further ado, we're going to show an example of how this works. We go over to manage. We hit Dynamo player. I already have it open.
Hey Mike, sorry to interrupt. Before you go any further, do you have to do anything special to enter the airflows, or is everything built-in parameters out of the box? There's nothing new to that process?
So in the new MEP template, if you just look at this fitting right here, this calc flow and calc node parameter, these will be in the new templates. There is an instruction file on how to add these to an existing project. This will be available, but it basically walks you through how to add these shared parameters to your job, and then the families for the tags are available in the Dynamo folder. So this takes you through, walks you through adding the project parameter, the shared parameters, and then the project parameters, so that you can use this software.
So that's for any job that's already been started, but like you said, it'll be in the template?
Correct, yep.
Okay, and so we're defining the node, the order of the nodes, and we're defining the airflows?
Yes, correct, yep. Each piece,
perfect, thank you.
go through, assign your node number, and assign your CFM. So I have it open already. Let's take a look. You're going to navigate to the folder where you're keeping the Dynamo script. In this case, we're going to use the static pressure calculator. We're going to click Edit Inputs. We're going to select Model Elements, which is all of this. We'll browse to the Excel sheet that we're going to output to, which is going to be this one. Then we have a couple things here. False for decreasing airflow, true for increasing airflow. So if you want to view everything from highest CFM to lowest CFM, click false. If you want the other way around, do true. And then if you're looking at exhaust or return, you should have this on false. And then if you're doing a supply, you can have that on true. So after we have that, we'll click play. And it takes all the physical data from the ductwork and the data that you gave it and puts it in this pressure loss Revit tab. So this is the raw output. VAV box comes out with a HVAC equipment or additional fitting. I do want to note that if you do skip a node number, it will put a blank line in for you. If you want to add something throughout the calculation, just skip a node number and it puts a blank line in. First thing we're going to do is look at number one, temperature, make sure our elevations are correct. You fill out all this. Check your supply, and yes, we are going from the inlet or from the supply point to the space. So check these parameters up here, make sure they make sense. Then we're going to look at our Revit items not included tab. You want these to read true. That means you didn't miss any calc node or calc flow parameters when you put the ductwork into the program. So both of those are true. That's good. And then we have everything that wasn't included in the calculation is listed down in this area. And we've and John's done some conditional formatting so that dampers and air terminals will turn a certain color to remind you that those need to be added in the calculation. So this is our raw from Revit. And then down here at Revit sample final, we've added in the smoke dampers, fire dampers, grill. So you have to add these items in after the fact to make for a complete calculation. In the future, there may be opportunity to take 3D elements for volume dampers and fire dampers, etc., and have this automatically do that as well.
Hey, Mike.
Yep.
I saw in the output of items not included that those were modeled as detail items. The volume dampers are a lot of times being modeled as modeled elements now.
Yeah.
So will that still not include it in the calculation?
Yeah, it'll toss them over here and they'll turn red. I was talking to Dustin about that today, and we're going to look at least making the volume dampers part of the program as well, so that they'll come in. But yeah, right now they'll just be dumped over here.
Okay, thank you.
Mm-hmm.
Mike, so you had blank rows between each line, like you said. You had to skip the node numbers, or did it automatically output with those blank lines? Because I guess the question I'm asking is, if I had to add in a fitting later and I just wanted to do it manually with one fitting, how easy is it to add in the volume dampers and any items that Revit didn't export, or anything new that I want to put in?
Yeah, so you'll go to your node number, which is this section tag here, and say I have a volume damper at the end of the run. You just come back in and you'll add it in, and it populates there. So you had a fire damper over here on this run of duct. You'll come back in, you add that, and it'll add your calculation. So you can see where we've done that on the Revit sample final, where the highlighted items have been added in. If you had a more drastic change in your calculation, what you have available to you are a couple tools. Calc node flow modifier for ducts. So what we can do is, say your CFM changed in a portion of this system. Say, I don't know, say here, for a certain section of the system, you need to change node numbers, or you need to input a fitting, or you have another takeoff over here. You can set an amount to increase the flow, set an amount to change the node value, highlight a bunch of items at once, and press play, and it'll modify them for you, so you don't have to go through one by one and change. We're going to look at now kind of a comparison between an actual calculation and balancing data. So we're going to try to do this pretty quick. Move this along here. This system right here is this system. We start off in a basement air handler supply down through a crawl space up into a classroom. Similar with the return, this comes through the mechanical room up and onto the first floor. The return run is here, makes its way over to the classroom, and then here's your first grade classroom. We're going to take a look at the calc for this. Just out of time, I have it up, but just for the sake of time, we're just going to look at the already output files that I have here, and those. So I have my air handler 6 Dynamo output. You have your return here. The highlighted items are items that I've added after the fact. That comes up with 1.06. And the supply. I want to note about, if you have one air handler and you want to have a bunch of pressure calculations in one spreadsheet, I would recommend starting with separate spreadsheets, for the Revit outputs, and then once you get them to a point where you're happy and you're not getting any errors, then copy the tab into an all-encompassing file. So if you look at these values we're getting on the return, we're about 1.06. On the supply, we're about 0.51. I just want to note really quick, this is the manual calc I did for this job, and they're pretty close, 0.52 and 0.99 on the return. So they're very close. But when we're looking at this system, we're not just looking at the supply and the return. I ran a quick calculation on the exhaust louver and the intake louver. And those pieces of ductwork are here. I want to mention that if you're doing just a run of duct without any takeoffs, you can just highlight this entire piece of ductwork. Sorry for jumping around a little bit here. You can apply a calc flow value and then call them all node number 1. You don't need to label each node in a consecutive order. And this will output to the spreadsheet and give you a pressure drop. It's not going to be in the right order, and where the order matters is where you have takeoffs and branches coming together. That's where the order of these pieces of ductwork really matters, and also for presentation if you have to show this to somebody. But if you just want to do a quick run of ductwork and get your pressure drop, you can do that without numbering each node. So if we look at the values that I got from this Dynamo script, I got the supply, the return. At the inlet of my via, I know I need 1 inch. And then exhaust louver run, about a 1/2 inch, intake louver run. So my total is about 3.28. But I need to take other things into consideration when I'm looking at this number. I need to think about the exhaust and the intake louvers. This is not a 100% outside air system. The ductwork can handle it. It's large enough to handle it, but it does create a little bit more of a pressure drop. Typically, we're only pulling 30% outside air on this system, so these values are going to be much less. And then you also need to factor in duct leakage. You know, what kind of contractor you're going to get. And I just want to we settled on 3.25 for the system, and I just want to give an actual balance report example. They put my design value in wrong. They put it at 2, but on the schedule we had 3.25 return fan, supply fan, and then the balance report came in really tight at 3.3 inches. So that's it. These tools, this spreadsheet John has is really, really strong, but it really need to make sure that you're checking it over, because you just need to make sure you know what is going on in your system and give it a nice look over. So a couple other design variables. When you're sizing your equipment, check the fan curve. Make sure you're not on the edge of a motor size. We all know stuff happens during construction. There would be an extra fitting, a little bit of extra pressure, maybe less pressure drop. If you have a bad contractor, you have a lot of leakage. Check that your motor size is not close to the next size up or down. And then think about the typical operating conditions, like I was saying. Where is this system going to function normally? And then think about, too, if your filters pack up in the air handler, is the fan going to have enough to overcome that over time? We're going to move into the pump head loss now, unless anyone has a quick question.
Mike, I just wanted on the spreadsheet that's on the network. I know we had the samples and examples, but we also included a comparison between a manual calculation and the Revit to just give you an idea of that they're pretty close to each other. I did a manual of that same system that Mike did for a Revit. That's under the Revit sample duct plant. And sample manual. Yeah, manual versus Revit comparison.
Right.
So, I did that manually. And, the yellow items are that were not included in the Revit run. And down at the bottom, you'll see the manual versus the Revit final is, the difference is like 0.033. They're very close to each other. And that had to do with items really 34, line 30, 51 and 53 transitions, because I put in a transition, which, Revit did not have. The way Revit takes a look at it, it assumes that there's a transition as part of any, converging or diverging Y. So any transition you have right as part or just immediately after Y fitting is considered part of that Y. This line here was different because you had a diverging Y and then a smoke damper, and then the transition down for the connection to the VAV box. So that I put in as a separate because it was, and that was a node that wasn't picked up as Revit, because Revit assumes that any transition downstream of a Y is part of the Y fitting.
So yeah, so in this case where something is separating this Y from, this is not a tight arrangement. There's a little bit of space right here. Whereas right here, you take off and then you transition pretty much immediately. In this situation, you have a smoke damper right after the takeoff. So you would still have your diverging Y main coming through here, but the duct size is going to be the same on the outlet of that Y as the inlet. Then you're going to have your smoke damper, and then you're going to have the transition in this type of situation.
Okay, that's it.
Someone has to keep doing that. Pump head loss, very similar to ductwork static. Air is a fluid, water is a fluid. Similar constraints with the surface materials, obstacles. The water is going to face resistance as it's being pumped throughout the building, and we need to account for that in our pump design. We need to make sure these are properly calculated. If you have a pump that's not strong enough, number one, it's probably pretty embarrassing. Number two, it's not going to make for a happy owner. 1 foot of head is 12 inches of water column, and a long time ago, a senior guy here got me to remember this by telling me that what's the height above your knee approximately? 2.5 feet, whatever. 2.31 feet. Height to above your knee is 1 psi. So it's good to remember this when you're looking between psi and feet of head. And I just want to have a side note. No matter you have an Olympic swimming pool of water or a 1/2 inch pipe, if you have a column of water, the psi, the pressure is going to be the same 1 foot down from the top of the 1/2 inch pipe as it would be 1 foot down in the entire Olympic swimming pool. So cross-sectional area does not affect the water pressure at any given depth. Similarly here, this is the exact slide that we saw before. And in the same way, we want to keep everything laminar. It's easier to pump throughout the system. Where are we going to get pressure loss in a piping system? There are a ton of different sources. The piping, the fittings, valves, control valves, air separators. This is a massive valve NASA's putting in. I think it's 96 inches. And our best practice is to maintain laminar flow. And some points of the system, turbulent flow will occur. Typically, that's going to happen at your coils, maybe in a boiler. And the reason for that is they're designed to actually induce some turbulent flow, because this is a lot better for heat transfer versus this. And again, we're going to control this Reynolds number, which is a unitless value of the relationship between flow and pressure difference. So through the diameter of the pipe, we can adjust the velocity, that should say water, and we can keep it in this zone by properly sizing the pipe to maintain a reasonable velocity. Very similar process here, and we're going to take a look at the pump head Excel sheet. The only difference with pump head is we don't need to worry so much about the order. There's not going to be a node number for each piece of each piece of pipe, because we don't have to be concerned with that with this type of calculation. So we're going to take a look at this really quick. So you're going to see a Revit items not included tab. That's standard for pretty much any Dynamo output. And then, John, you made some updates to this spreadsheet, right? The MPSH calc?
Yeah, net positive suction head calc. The temperature cell used to actually reference the temperature on the pump head calc. And now I have it reference the temperature you input in this actual sheet. You know, just in case you're using the sheet and you don't happen to put a temperature in. And also the fitting types and quantities were not actually fully calculating through, and I corrected that. That's the change that were made for the updated spreadsheet that was posted about 2 weeks ago. The one just posted today now includes that Revit not included chart, and it's also added some additional pressure drop line items for, you know, triple duty valves, suction diffusers, air separators, as such, that were not in the original spreadsheet.
So similarly, we model the entire system in Revit at the proper sizes, isolate the critical run through a similar method, filter or copy to a blank area in a detached model. We're going to fill in the calc flow parameter for each piece of pipe and fitting. And as I said, the calc node is not required. In our spreadsheet, we do not need to account for the transitions between sizes and the arrangement of those pieces of pipe and fitting. So after we actually export this, I just wanted to note this spreadsheet has not been modified to accept this information. It's just taking the physical data and putting it in. You're going to review your calculation, enter your fluid temperature, check your pipe materials, enter a glycol percentage if you need to. Again, hotter water is tougher to pump, and water with more glycol in it is also tougher to pump. So we need to make sure that those are in there. All the T's in the piping system are outputted as straight T's, as in you're going straight through a T and it's branching off to the side of the critical run. There'll be a few instances on your critical run where you have side outlet T's. You need to go in and account for these and add them in at the end. These will be the minority versus a straight T. And then you're going to add valves, sudden entrances, sudden exits, any other special fittings that we're going to talk about in a second. I'm going to just show you a quick example. This is the chilled water system from School 10. And actually, we're going to look at this one first. This is actually one of Adam's jobs. This is Uncommon Schools. This is the critical run. And it's been parsed out in 3D and then tagged with the GPM in each piece. So all we're going to do is we're going to go to our Dynamo player, do our pump head calculator, select this pipe run, and browse for our output file where we're going to put this information. We're going to choose this file here. While this is running, I just want to note, you should label your output files, your calculation files, with your project number, what you're calculating. And I'd recommend printing off some to-scale plans of what exactly you calculated at that time. In some projects that I do, I have different phases for my calculations, DD, CD, so that I can see if pump size has changed over time, or I can have a record of the calculations that I've made on the project throughout a point of time. You can add a date code to your output, whatever is most comfortable for you, but you want to make sure that you have a record of what was calculated at that time and what your results were. So that's completed. If we look at the results, it outputs the sizes from highest GPM to lowest GPM, and then the lengths of each size. This one went all the way down to 3/4. Again, you're going to add in your side outlet T's, which were just a couple in the system. You're going to add your ball valves, check valves, any of these other items. We're going to take a closer look at that on this other example for school 10. How am I doing on time? We're doing all right. Take a look at this one. Pump head calculator. Same process here. Highlight it all. And I'll put it to our named file. We'll run that. And then we're going to get into some of these other items that you need to calculate in your system. While that's running, we'll take a look. Triple duty valves, air separators. What is a C sub V? I always found it pretty easy to look at the cut sheets for these types of items. Some items like control valves give you a C sub V value, and it was a little bit confusing for me for some time. The C sub V is a number of GPM that will pass through a valve with a pressure drop of 1 psi. There's some calculations here, or equations that you can use. But if we look at a cut sheet of a control valve, typical Belimo control valve, it's got a C sub V of 77. That's telling me it can flow 77 GPM at this size with a pressure drop of 1 psi. Obviously, if you flow more, you're going to have more of a pressure drop. If you flow less, the pressure drop is going to be less. Taking a quick look at like a triple duty valve. These always come, this is a Takeo. These come with a nice chart. Okay, you got your size of each valve. You're going to follow your curve down. Where's my flow? And then track over to your pressure drop. You're going to add that into your calculation. Similarly, with an air separator, they typically have a nice chart. Here we go. Pressure drop, water velocity. You're going to calculate that out. You're going to look at the size that you need and what's a comfortable pressure drop for you in your system. So now that we've got, that should have finished by now. It did. And again, it outputs everything. However many different flow rates you have, it's going to output to the spreadsheet. But then there's a lot of work we need to do down here to finish this off. I have a finished one done already of this chilled water system pump head. So we had a heat exchanger loss at the air handler, air separator loss, balance valve. There were 2 triple duty valve, suction diffuser. This is an older spreadsheet, so it's different now, the way these rows come in, so that you can separate this stuff out. I have a buffer tank on the system. I have a 3-way control valve. And I came up with 73.7 feet of head. The pump was spec'd at 80 feet of head. And my balance data came in right in at 76.23. So these spreadsheets are accurate if you use them properly. I mean, very, very, very close. I mean, that is great. You always want to account for a couple things though when you're designing these systems. A couple of design variables that we can look at here is if your system has a lot of 2-way control valves, you need to make sure that your minimum flow is going to be maintained. You can have a very violent situation going on at the inlet of your pump, if you don't give it the minimum flow that it needs. So in this system, the one I just showed you, I have one 3-way control valve on the chilled water system to make sure I maintain my minimum flow. If you don't maintain your minimum flow, you're going to deadhead the pump, and you're going to make it cavitate, which is basically the pressure at the suction side of the pump is going to drop below the vapor pressure of the water, and then the fluid pretty much boils. There are bubbles everywhere, and then those get into the impeller and then literally collapse on each other at supersonic speeds, and they destroy impellers like that. So this is water doing this to a metal impeller. So when you're designing your system, check your pump curves and motor sizes. Again, make sure you're not on the edge of a selection. Make sure you're not teetering, on either end. Account for some additional offsets in your actual system itself, the way it's installed. And then you want to size your pump for a design day, but when you're looking at the efficiency of it, you may look at having the peak efficiency at more of a 70% area where your pump's normally going to be operating. It's not always the design day. The majority of the runtime of the pump is not going to be on a design day. And so making sure that the pump is efficient on a non-design day is very important. Any questions on pump head before I move into system volume?
Mike, you want to just open up the spreadsheet? I'll take a quick comment on that NPSH tab.
Yep.
Yeah, the NPSH sheet
There you go.
is net positive suction head. On any of your pump curves, there's actually a matching curve that says the minimum pressure that you need for that pump so you do not have boiling of that water. So this is for an open system where you've got a pump that's pulling from an open tank. This is for putting in the information for the fittings and whatever, and down at the bottom of the spreadsheet, the elevation differences between where the pump is and the where the pump location versus the elevation of where you're pulling it from, your temperature and everything, to then tell you what is the available head at that pump inlet. And you check against the curve to make sure that that number is higher than the minimum that's listed you're required for the pump curve. This is open, applicable to an open system where you're pulling, from an open tank. Thank you.
Thanks, John. So last thing we're going to take a quick look at, this likes to pop up on this side. All right, the last thing we're going to take a look at is system volume. Another important aspect of designing any water system. This was always a fun thing to do. I remember coming in as a co-op and doing a few of these with a ruler and a highlighter and measuring the lengths of each size of pipe on a job. This tool is going to make that a lot easier. So what does an expansion tank do? We have a bunch of fluid in a closed system. It's going to expand and contract with temperature, and you don't want to subject your system to excessive pressures and blow relief valves. This helps alleviate some of that pressure. Oops. And so designing this is an important aspect. So you have a bladder in here. You're going to pre-charge your tank with compressed air or another inert gas, and the water is going to interface with this bladder. So as this water in this pipe expands and contracts, it pushes against this bladder, and the air takes some of the pressure away. So this is definitely a critical part of your system, especially for older systems that can operate up at 210 degrees. We don't design that way anymore. But if you come across something existing, you could have a fill temp of 40 degrees and you can heat that up to 210, and that's going to be a very large volume difference. This is a similar workflow, model the entire system. It's important that everything's modeled at the right size, of course. If you're like me, sometimes I like to just model it quickly, and maybe sometimes the size won't be exactly right, and then I'll find myself going back and revising that. So make sure everything's modeled at the right size. You're going to isolate just the piping system, and we're going to take a look at what that looks like right now. So this is another job, Adam's job. Uncommon schools, area C. This is the piping system, and it's a very similar process. We're just going to go to the tool that we want, piping system volume, edit the inputs, select all this pipe fittings, browse to the file that we want to take it to, just here. Run that. So this information is going to go to a tab on the expansion tank spreadsheet. And then we're going to copy that into our expansion tank size. So let's take a look at that. It's going to come out right here under Revit export. You got your pipe size and your lengths. It also gives you a pipe fitting volume of 5 gallons, 5.5 gallons. So you can put that in too. But if we take these values and put them in here for your lengths, it gives you 105 gallons. Then you're going to go through your equipment, boilers, coils. John has some rules of thumb here for gallons per MBH for these unit heaters, fan coil units, fin tube, convectors. They don't typically have volume listed on their cut sheets, so John has some shortcuts here to follow. Miscellaneous. Go ahead, John.
Yeah, those rules of thumb really came, as I recall, from Bell and Gossett Little Red Schoolhouse manuals.
You may be able to find information, but if you can't, definitely you have to account for these pieces of equipment in your system. I'll throw in the 6 gallons for the fittings on miscellaneous. So, and then we get to these final steps here, system height. So think about this. When you're filling up a brand new system, probably from a boiler, mechanical room in the basement, you're going to have an air vent at the top of the system. And this height that you're looking at here is going to be from the fill point or the lowest point of pipe. Doesn't necessarily need to be the fill point. It could be the lowest point to the highest point. So the system height, let's call it 30 feet. That gives you a fill pressure of what you need if you were filling it from the bottom to be able to fill the system. This is the pressure that's set on the plumbing backflow device and is given to your system as makeup water on the outlet of the backflow device. There's the guideline here for the relief valve fill pressure plus 15 to 25 psi. So we'll do 35, call it. System fill temp could be as low as 40, and then if this is a hot water system, 180. And then your pre-charge pressure. Every tank with a bladder has a pre-charge pressure, and if you want to modify that pre-charge pressure, you're going to want to make sure you note that on your drawings. You would input that into this cell here, or if you can modify your initial tank pressure, typically fill pressure is a good one to start with. So then that gives you your required tank volume here, 10 gallons. And you have your selected volume. John, anything you want to add to that?
Now, I think under where I have not less than 12 psi, and like, but not less than 30. Those are values that are built into the formula that if you don't have those, at least the formulas really don't work properly.
One more thing I wanted to add, I'm going to just backstep right here, is on the pump head. When you're doing a glycol percentage, this does not affect these values. These values from your equipment, you're going to want to look at the glycol correction factors and put those in. This propylene glycol percentage only affects the pressure losses through the piping and fittings. So I just wanted to note that. And that's what we have there. We'll take any questions anyone has. Pretty good on time.
Hey, Mike, can you go back to the duct plan for Revit calculator? Just go to the Excel file. And if you could show that layout next to the Excel under the Revit sample calc. I'm looking at node 19 and 20. So on your plan, you've got 19 is a straight run, 34 by 16. And then it looks like you have a branch that's 100 CFM.
Correct.
And it looks like you have a split line coupling and then node 20. So you're pulling 100 CFM off a branch, but you're not reducing the main size. So do we have to make sure that we put in a split line coupling to get the calculator to handle that appropriately?
That's a great point, Adam. So anywhere in the system where you want to change your CFM and you don't necessarily want to make a size change, just throw in a union, and that way you'll have the right length of 4600 CFM duct and the right length of 4500 CFM duct in this situation. So yeah, you throw the split line coupler in. It doesn't throw it in the calculation anywhere. I think it actually comes out on item not included. It should. There it is right there, rectangular union. It doesn't include that. It's not causing pressure drop. But yes, if you have a change in CFM and you're not changing your size, then you're going to put that split line in there and change the CFM for each node. Thanks, Adam.
Okay, great. Just want to make sure I understood that.
Yep.
Hi, this is Ryan. I have a question.
Yep.
Do you have view templates for when you duplicate your views to isolate either all ductwork or all piping so you can not have to, like, I guess, manually clean up the view to prepare it for your tagging?
That's not something that we have right now, but that's a good idea to have. Potentially in the future, something we could do. Like I was saying, sometimes you want to do a filter and just highlight the run of duct and everything else associated with it, and then add, say, a comment to it, and you can filter, just duplicate a view and then filter that view by that comment so that only that critical run shows up. That's worth a thought, Dustin, if maybe we wanted to put something like that in.
Yeah, we can look at that.
Yeah.
Hey, Mike,
Yeah.
on your air pressure drop calc on the presentation, you had said you added an additional 1 inch of drop for the VAV box. Is there a reason you did that, or did you just not go anywhere downstream of the VAV in your calculation?
I knew I needed an inch at the inlet. Oh, you know what? I think I noted that wrong on the drawing. That's a good point. So if I had a 1/2 inch of drop to the inlet of the VAV, then I'm looking at a minimum of 1 for my supply fan. Or sorry, 1.5 for my supply fan. No, that's in there, right? So when I selected the VAV, it expects a 1 inch of static pressure at the inlet. So it operates as intended with the pressure drop across it. Some VAVs, as far as I'm aware, don't function properly and sense the pressure properly unless they have enough pressure at the inlet.
Okay, you're right. But so you're supplying that 0.51, that doesn't include anything downstream of the VAV. That's just up to the inlet.
No, so there is, yeah, it's just up to the inlet. There is ductwork downstream of the VAV here.
Okay.
But I'm comfortable with having that inch at the inlet and being able to overcome the losses on the downside of it. I could have included this into the calculation, and it would be good to. You could definitely do that. I think on this one, I just took a quick look and noticed that I had enough to get to the end of one of these diffusers. But definitely, if you have more of a complicated setup after this VAV, I would definitely factor that in and take that as my critical run. I would calculate for the 1 inch that I need at the inlet for the VAV to function properly, and then look at the
Yep.
pressure drop across the VAV. There'll be some sort of pressure drop associated with this VAV, and then whatever I have left, I need to make sure that it gets to the rest of this critical piece.
Okay. Thank you.
Thank you. Anybody else have any questions? If you want
Are
to
there
use,
any lessons learned or suggestions anybody has when you're going through stuff like this?
I didn't quite catch that, Brian. Were you talking to me? Sorry.
I'm just talking to everybody. Are
Oh,
there
okay.
lessons learned that anybody has, or some items you picked up along the way that would be good to share with everybody?
Mike, I did
Yeah,
have a
this is-
question. Oh, go ahead.
Sorry, this is Ryan. I think one time I neglected to consider, there was a plan of return, and I neglected to consider all the, like, I didn't necessarily carefully look at the reflected ceiling plan to consider like where all the full height partitions were. And it created pressurization problems. And so there was, so it wasn't a ducted return, but I didn't necessarily consider thoroughly the return path of all my air. So it did create like pressurization problems, and all that to say is even if you have a certain return duct, like going through from like a rooftop unit in one area, you have to go through to another to, even if you're doing like the duct static pressure drop, to consider the return path from all the spaces back to at least your point of return.
That's a great point.
Yeah, that burned me one time.
Mark, did you have something?
He had a question on the pump head calculator spreadsheet.
Yeah.
That glycol correction factor is not applied to the overall
It's
pressure drop. It doesn't include the fittings or the
no.
triple things like that.
It includes, so this glycol percentage will only affect the pressure losses from the pipe and the fittings. All
If you
of
look
these-
down, there's actually that highlighted note there that tells that. You
Right
know,
there.
it's not being applied to what's listed there for like a chiller or heat exchanger. The assumption is that, you know, when you get that selection from the vendor, you know, you're telling him, you know, that you've got a glycol system. He's giving you the pressure drop, you know, based on the fact that it's a glycol system.
Sure, for the equipment, but that would also apply to the valves and things like that. Triple duty valve.
It is being applied to the valves.
It is? Okay.
Yes,
I don't think
just
so,
not
since
the
it's part of
equipment.
pressure drop. Okay.
Yeah, it's not applying to this triple duty valve.
Yes, it is. Yes, I have it applying to the balance. Yeah, I have it applying to everything, you know, from air separation.
Minus the equipment.
Oh, okay.
Okay.
All right, awesome.
It's just not anything for the chiller, the heat exchanger, or those manually input lines on 79 and 80.
All right, perfect.
Mike, I got another question for you here for the ductwork static.
Yeah.
For the diverging, converging Ys, any of the fittings that we're modeling in Revit, they're tied, they're coded to work with the Excel file. So if we're, you know, looking at your layout, it looks like the main Y in Excel is tied to a transition in Revit, correct?
Any transition in Revit pulls up a Y fitting, correct?
And it's a main
Or
Y.
tab,
But if you want
or
a branch Y, as your critical, it's going to look for the boot tab?
That's correct. Yes. Yep.
What if we use, what fittings do we have to make sure we use in Revit? Is it, because what if we pull in an out of the box fitting that's not in our template for a specific instance? For example, we have a transition elbow that we want to model for a 90-degree. Is the Excel file and your Dynamo script only looking for the 90 or the mitered line vane representation, or will it use any of the fitting families that we pull in?
As long as it has elbow in the name, it'll pull it.
Okay.
And then it'll look for the angle associated. Right here, angle.
Okay. So there's a couple tips and tricks on family names for fittings then to make it work, but we can use custom fittings or out of the box fittings that aren't in our template as long as they're named appropriately.
Correct. If it's a transition, it has to have the transition name. If it's an elbow, it has to have an elbow in there.
Got it. Okay.
And if you have something specific like that, just let me know. Sorry.
So it's looking for transition for a main. It's looking for elbow. What language is it looking for a branch? Tap. TAP?
Yep.
Okay. Thank you.
Thanks. If you have something one-off too that it won't work or has a different name and you don't want to modify it or it has some special parameters, you could always hit me up and we could take a look at it. Wouldn't be too hard to modify what it's looking for. Any other questions anybody has? If not, I appreciate everybody stopping into our virtual meeting here, and hope everybody's doing well, staying safe. And if you want to get a hold of me with any specific question, feel free to. And hope everyone has a good day.
Mike, I think I just want to add, you recorded this session?
I did, yep.
So I think this actually recorded session is going to be saved to the network. So if somebody wants to view it again.
Yes, it will.
Hey, Mike.
Thanks, Mikey.
Thanks, everybody.
Thanks, John.
Thank you very much.
Take care.
Thanks, guys.
Thanks, Mike.
I just buzzed through the instruction manual. I think it might make sense to add the requirement for the elbow, transition, and tab. Just a little verbiage saying if you use something not in the template, that it has to be named a certain way.
Can definitely do that, Dustin. Coming in really quiet, by the way.
This mic sucks, man. I don't know what.
Very quiet. Very quiet. All right, I'm going to end the meeting. Thanks, everybody.
Thanks, Mike.